All right, so let's talk optics. So optics and photonics is my area of research, and so it's something I'm passionate about, of course. And so today we're going to build an optical projector. Before we do that, we first have to understand how refraction works. So many of us are wearing glasses. The principle of how glasses work is that they refract light. So refract means to bend. And so they allow light to focus on our proper parts of the eye. So I first want to start off this activity with an example where imagine you're a lifeguard and you spot someone in the water not doing so well. All right, so this is the coastline, this is beach, this is water. Okay, has anyone been a lifeguard before? No one's. Children, yeah, children, you gotta always be on the guard. So if you're a lifeguard and you see someone. Oh.
Children who are lifeguards.
Oh.
They are true lifeguards.
Mm-hmm. So let's say that you're on the beach and there's someone not doing well in the water. What path would you take from your lifeguard station to this person to help them as quickly as possible? How many people would go in a straight line? Fastest path is through a straight line. So we'll see. So this is the shortest distance, but is it the fastest? Okay, you travel faster on land than in water. So I run. I'm a marathon runner, so I can run about 8 miles an hour for a typical race. If I'm sprinting, I can get up to 10 miles an hour, maybe 11. In water, I used to also swim. So in water, I can swim like a 17, 18-minute mile. So I'm swimming at about 4 miles an hour. So I can definitely run much faster than I can swim, right? So knowing that information, how would you change the way that you would approach the problem?
I'm sorry, can we go back for a second?
Sure.
Because I want to make sure we're all on the same page. Your question was, which way would you get to that?
Yeah, so I'm the fastest way. I want to get from here to there.
So I'm going to bring this back. That's the hypotenuse. That's the longest distance. You draw that.
So this distance versus this distance?
Yes, because
This distance it's the hypotenuse. It's longer than an individual side, but it's shorter than the sum of the two.
Right.
Yeah.
Run faster, you should run down the beach.
Yeah. So should I run down the beach and go perpendicular like that?
That's what I would do.
Okay. Other suggestions?
It's probably somewhere in between because
Mm-hmm. So something like that. Yeah, so that's the correct answer. You want to go somewhere between a straight line and this angle such that it's perpendicular. And so why is that? It's a trade-off between how fast you can go and how far you can go. So if I were able to run millions of times faster than I can swim, then I want to minimize how much time I'm swimming. So if I can run like a million times faster than I can swim, I would go exactly this path and then go perpendicular. Let's say that I'm crazy and I'm a super fast swimmer. I'm Aquaman, right? And I can't run on land. In that case, I would go along this path and then go along that path. If I can run and swim at exactly the same speed, I would go the shortest distance along this line. So the path I take really depends on the speed in the two different materials. And this is exactly how lenses work. So a lens, or even just an interface of, let's say, air and glass, light travels faster in air than it does in glass. So the speed of light in air, 300 meters per microsecond, approximately. In glass, it's reduced by about a factor of 1.4, 1.5, depending on that. So typically, if I have, let's say, sunlight, and I look, it's going to refract at an angle. So we work with the perpendicular to the surface between the air and the glass, and we measure angles relative to that perpendicular line. So we talk about this incident angle So it's this nice Greek symbol. It looks like an oval with a line across called theta. So the line that we come in at is called theta incident. It's the incident angle of the light. The light gets bent at the interface of the glass into a new angle measured relative to this perpendicular called theta out. Sometimes this is written theta 1, and this is written theta 2. And Snell's law is basically a solving of the question, what path is the shortest distance from one point to the other? It's also a way to solve what are known as Maxwell's equations, which talk about the relationship between electric and magnetic fields that explain how light propagates. So this solution to the equation allows us to calculate what angle does the light bend at. If you ever look at a glass and you have a straw in the glass, does the straw look straight? No. It's like it goes for a while and then it's displaced and then it continues. This is a result of refraction. So what we want to do in this activity is teach students how, or have students explore, how does the angle of incidence affect the angle of refraction? And in order to do this activity, we're going to shine light at a block of glass that's mounted on a protractor and measure what is the outcome angle as a function of the incoming angle. The relationship says that if this material has a refractive index n2, so the refractive index is the ratio of how fast it's the ratio of the speed of light to how fast the light travels in that material. This is the ratio of how fast it travels in vacuum compared to the velocity in this material. Snell's law tells us the relationship of these two angles in terms of these refractive indices. So the refractive index is a ratio of how fast or how much light is slowed down when it travels in a material. And it's a relationship that says that n1 times the sine of the angle theta 1 equals n2 times the sine of the angle theta 2. Now, in order to appreciate this formula, students need to know what sine and cosine mean. So there's a review session or a review section in the book that talks about waves and sines and cosines. How we will introduce this to the STEM club is something that we're still trying to figure out. So the question of whether we first talk about here's sine and cosine and now you do this activity, or you first do this activity and we give you a table of what sine and cosine is and you just accept it as the truth and later on you discover what it means, that's something that we're still trying to figure out what the best way to do is. So what we're going to do in our activity, we're going to have a block of glass, we're going to shine light from a laser beam, and we're going to see how it refracts at the interface of air and glass.